All right, so we're gonna, in organic chemistry, we'll learn a number of techniques, and one of them is recrystallization. It's typically a later step in a synthesis that we do, where we're trying to basically purify a solid organic compound, right? It's also typically a step that we could do after a liquid-liquid extraction, for example. And we'll encounter a later experiment in the term where recrystallization, is a later step. But what the idea of recrystallization is that we have a compound and that compound is impure. It's in a solid form, but it has some impurities present. So what we're trying to do is recrystallize it. Actually, I don't know if you guys see the mouse. So what we try to do is recrystallize it, right? It's not a chemical reaction that is taking place. We're simply trying to get rid of some impurities, and what we're looking for is a pure compound. We also want that pure compound to be a crystal, so we want it to be in the solid phase as well. So we have to think about, what type of change can take place where our pure compound of interest could still be in the solid phase, but then our impurities are no longer in the solid phase, right? So that change can actually take place if we think about it. Oops, I keep pressing the wrong button. All right, so that change can take place really if we have the impurity in a different phase, and in this case, in the liquid phase, right? So how could you take a compound that was originally a solid, and at the end you also want it a solid, right? So you have to dissolve it in some things, and what we take into account is differences in solubility, right? The technique itself involves taking this solid impure compound, and you do want it to have a minimum amount of impurities. If it has a large amount of impurities, recrystallization is not the best technique, but we take it and we want to dissolve it in a specific solvent. So the only way those impurities, so if it's originally in a solid, then those impurities are part of the crystal of the compound, right? They're all solid. So the only way to separate the impurities from the pure compound is that you want everything to be in the same phase, right? And that would be to make it soluble in solution, right? And then you want the choice of solvent is really one where the solubility of the compound of interest is temperature dependent, right? Whereas the impurity will always remain soluble in solution, right? So what we do is we dissolve that compound in a solvent, but because it's temperature dependent, we typically want to dissolve it in a hot solvent, right? Which would make the impure compound soluble, right? And then we allow it to cool slowly, right? That would cause the compound of interest to be insoluble in solution. So we end up using a minimum amount of solvent as well, but we'll talk about that. And then we filter impurities remain soluble in solution. Let me move this up here. And again, right? So we want the compound of interest soluble in solution. One specifically, that solvent is hot, and we call that the recrystallization solvent. Then we want it insoluble as the solution cools down slowly, and then that's how we're recrystallizing it, collecting the crystals, right? So the technique itself now involves dissolving an impure solid in a minimum amount of hot solvent, and then we're filtering it to remove any impurities, right? We're allowing the solution to cool down slowly to room temperature, and then the pure crystals of the pure compound will basically begin to form and separate out from the solution, and we can collect it as crystals, and then we can characterize it. A quick way is just running a melting point analysis. Another way, we could run a proton NMR on it as well. Okay, any questions on the technique itself? Okay. So this video will really focus on the technique. The experiment itself and the detail is on the video. So what exactly is the process? What you'll do is you weigh an impure solid, right? It has, however given amount of impurities. We're gonna place it in a flask, and then you've already tested what would be a suitable recrystallization solvent. Solvent. Okay, so suppose you have a compound of interest, you have no idea what would be a good recrystallization solvent. Now that would be a whole set of experiment that you'd run to figure out what would be the best recrystallization solvent. But you would take a small amount of that impure compound that you're interested in, you dissolve it, let's say in small test tubes, different types of solvents at room temperature, and you'll see would it be soluble or not. If it's soluble, then that wouldn't make it a suitable recrystallization solvent because you want it to be insoluble at room temperature. If you heat it up, it's soluble, perfect. Then you would cool it down slowly and see would it remain soluble or not. Right, but remember, it is temperature dependent when you pick your recrystallization solvent. All right, and then what you want to do is allow it to cool down slowly to room temperature. And cooling it down slowly is very crucial that the crystals that are forming are those of the pure compound. And the whole process is really an equilibrium process where the molecules are in solution. And they're in equilibrium with molecules that are forming the crystal lattice structure. So you have, I'm just gonna give an example. Actually, let's just draw it. All right, so you have molecules in solution. And then those molecules in solution go in and begin to form a crystal lattice, right? But what they'll do over time, since it is at equilibrium, they'll form the crystal and then they'll basically dissociate back in solution, and the process is in equilibrium until that crystal, begins to grow, and then it will more so favor the forward direction, right? So allowing it to slow down slowly is very important when it comes to excluding any of the impurities, right? And remember, a crystal structure is a highly ordered structure, so it will tend to want to exclude impurity, right? To kind of promote that, you would allow it to cool down very slowly to room temperature. And then, right, you could also place it in an ice bath. If you watched the video that was posted, you would have noticed that the crystals began to form while it was at room temperature. Right? Well, once you've had the crystal, what you'll do is we'll use a vacuum filtration, and we have a filter paper right here. We have to pre-weigh the filter paper, or what I did in the experiment is I took that top part of the Buchner funnel off and weighed it, pre-weighed it. And then you'll pour the solution right in, you'll turn the vacuum. What will drip down here is you want to wash it with a small amount of the recrystallization solvent, but you want that to be cold, right? Because remember, the compound of interest is soluble in the solution when the solution is hot, or when that recrystallization solvent is hot. So what you want to do is wash it with a minimum amount of cold solvent, right? And then what drips down here is what we call our filtrate, right? And that would have our impurities. Our impurities would be soluble in the filtrate, whereas our compound of interest has recrystallized, and we would collect it right within the Buchner funnel. We have to allow it to dry for about 15 minutes. It would help sometimes if you take it out of the Buchner funnel and kind of put it on a weighing paper and then you could put another weighing paper on top and dry it through a weighing paper. It wasn't dried sufficiently on the experiment that you saw on YouTube that was posted, which is why that weight was slightly higher. I mean, it was high, right? So if you calculate percent recovery, you would have noticed that it's higher than 100%, which is really due to not being dried sufficiently. Okay, and then in any experiment that we run, we typically want to characterize the final product that we get. Was it pure? Was it impure? Did we get what we expected? Could we run it NIR? Are we looking at different reactions, different functional groups that are appearing and disappearing, right? We could simply run a quick IR. NMR is always one way to assess the purity of something, but for us, melting point analysis is a quick way to assess the purity of the compound, right? And typically, if it's narrow and within 5 degrees, you could say that the compound is pure. So let's see. We're taking the flask off the heat source and placing it on the bench top to cool shock the crystals. Yes, in a way. If you had it on the hot plate and the hot plate, was warming it up, and you once of a sudden put it on the bench top, the difference in temperatures is quite a bit. But in this case, it doesn't. But you could always keep it on the hot plate to cool down as well. Right? Good point, Nicholas. Yes, so typically the melting point, so what we do is we have our little melting point capillary tube, and we have the solids, right? And as soon, when we measure the melting point range, as soon as we see any part of the solid begin to dissolve, and that's our initial temperature, whatever it is, and then we wait until we see everything completely melted, not dissolved, and then that would be our second value that we take, right? So that would be our melting point range. Just call it X and Y, right? And if the actual melting point, the theoretical melting point of this compound that we're running the melting point analysis is within 5 degrees of the actual, if this range is within 5 degrees of the actual melting point of the compound, then we could say that it's pure. But the narrower the range, the more pure that product is. Okay, so if our compound of interest has a melting point of 174 degrees Celsius, and then we run the experiment and we get a melting point between 165 and 172, then we could say that it's impure. But as long as it is within 5 degrees of 174, typically that indicates that it's pure. Right, on the YouTube video, I had the text and then the melting point doesn't show, but once you take the actual quiz, you'll notice that the melting point is included on there. I believe I included it with the conclusion prompt as well. Okay, well, in this experiment, what you're focusing on is, or what the experiment focuses on, is recrystallization of NBS, right? Succinimide is the impurities that is present. You start with crude NBS, water. It was tested that it would be a really good recrystallization solvent. And then we're collecting it via vacuum filtration at the end. Right? I won't go over the actual details of the experiment since it is on the video, but the process mainly, if you understand the process well, then going through the video will make a lot more sense. Right, so that's all I had. Any questions? If you guys feel like going through the actual experiment in detail, aside from the video, I could prepare that for next time. If you know the YouTube video alone is not sufficient, but for the most part, I'll mainly focus on the background of the technique that we're running. All right, any questions? Brittany, would you like to add something that I may have missed?
Can you hear me?
Yes.
Okay. I had a question earlier. Is the grade for the discussion post this week going to be based on the back and forth between the students, or is each student supposed to make a post, say what they think, and then the leader summarizes that in the end? Do we want
so
or
right. So they're being graded individually and overall, right? So the summary is basically everybody else's, comment is going to be summarized, but it's I'll mention exactly how, but they're being graded on both. So if someone barely says anything, doesn't try to analyze why that solvent may be appropriate or not, then they wouldn't really get the point, even if the entire group at the end had the correct analysis, right? So everybody has to have some effort on the individual effort on the discussion board to be able to get the effort of the entire group. So if you're the team leader, no, you're not doing the analysis on your own. Everybody is, right? You are as well, right? So everybody is kind of analyzing it and somehow, in some way, and then the group leader is simply summarizing it. Right? So basically, everybody has to contribute to the summary that the team leader will post. The experimental melting point is on the discussion. I believe for the recrystallized NBS, it was 173 to 174. Okay, you should notice it right within the quiz, right? Right within the writing prompt for the discussion. And it's on one of the quiz questions as well, that I did give you the temperature.
Hello.
Yes.
So I had a question about how often this experiment is actually used, because it kind of seems like the limitations are for really specific scenarios. So how often in a lab would this actually be beneficial to use as a purification?
So if you run the melting point analysis, sometimes before and after recrystallization on a synthesis, you could you'll notice that it was more pure after recrystallization. How often is it used? It is a common technique for purifying a compound. It is one of the more common techniques. It's not suitable for every synthesis or for every experiment that's being done. But should you run, a synthesis, get the final product is impure, you have an idea of what type of impurities are present, then recrystallization might be the way to go, right? You could tell that impurities are present from melting point analysis, from proton NMR, from running NIR. Right? And typically a single solvent might not do, where you'd need to use 2 different solvent systems. Right? But it is typically a simple and effective technique for purifying organic solids. All right, any other questions?
Hi, I have a question about the discussion.
Mm-hmm.
So my group just commented and did everything, but it says that the team leader is supposed to summarize. Is the team leader also supposed to comment and give
So you could comment if you feel that they something was missing. Yes, sure. If you feel like everybody's post doesn't, something is missing within everybody's post for the analysis, then you could definitely comment on that, or simply include it within the final comment. That's fine as well.
All right, so the final comment from the team leader would just be like a summary, like this solvent.
Perfect. Why and why not? Yes.
Oh, perfect. Awesome.
And the whole idea is that someone else might have said something that you didn't think about, or someone might say it better than someone else, and as a group you'll come up with a better summary.
Okay, thank you.
You're welcome. I didn't need to stop share.